My people, hope we're doing well. This is the second video on related rates that are based on two-dimensional geometry. This one obviously deals with a circle. I went ahead and I cheated. I didn't freehand that. I used a small cup from my kitchen. If you're a stickler, break out your compass. But let's go ahead and talk about this one. A stone dropped into a still pond causes a circular wave. Okay? Let's go ahead and draw the radius, and so we have r. Assume that the radius of the wave expands at a constant rate, so my given here is dr dt, the rate at which the radius changes with respect to time. It increases at a rate of 2 feet per second. Okay. Now, this then asks us 4 questions, so let's just go down the questions one by one. Okay. Question in part A is how fast does a diameter increase? So it's looking for dd, dt. Now there's no conditional information on that, so we have to assume that it's either not needed or it's implied somewhere else. We'll get to that here in just a second. How fast does, in part B, how fast does the circumference change with respect to time? And of course, it again gives us no conditional information. Part C asks us how fast does the area change with respect to time when, okay, and here's the conditional. I'm going to combine the condition with the questions. So when r is equal to 3, and then d is going to be again dA dt, but it's when a is equal to 8 pi. So we have 2 questions that don't have any conditional information and 2 that do. Well, we're going to see why part A doesn't have. Now, you can probably figure it out just intuitively. Now, if the radius is expanding at 2 feet per second, then the diameter, being twice that, expands at 4 feet per second. But remember that it's because the diameter is equal to 2r. And when I differentiate, I get dd dt is equal to 2 times dr dt. Now notice that neither of these are to a degree that is greater than 1. So when I differentiate, they both disappear. There's no d left over. There's no r left over, which is why I don't need a conditional piece of information right here. I have everything that I need. My dd dt is simply 2 times dr dt, which is 2 feet per second, and therefore it's 4 feet per second. And ta-da. Now part B is similar in the fact that its c is equal to 2 pi r. And since neither of those are to the second degree, they both disappear in, there's no chain rule basically. They disappear in the differentiation, and I'm basically given 2 pi times dr dt, which is 2 feet per second, and I'm left with 4 pi feet per second instead of just 4 in this one. Now it changes when we get to C because the area is equal to pi r squared, and you can already tell that when you differentiate this, you're going to get dA dt is equal to 2 pi r dr dt. And it's that r that's left over that requires this little piece of conditional information, right? And so dA dt in this case is 2 pi, r is 3 feet, and dr dt is 2 feet per second, and therefore this winds up being 12 pi feet squared per second. Now this next piece winds up being a little difficult because I don't have a place to plug in. I'm going to be using this same dA dt, right? It's still about area. 2 pi times r times dr dt. But this a, this area value, implies a particular r value. And because 8 pi is equal to pi r squared is equal to 8, and r is equal to 2 root 2. And so this one simply becomes 2 pi times 2 root 2 feet times 2 feet per second. And this actually winds up being 8 root 2 pi feet squared per second. And it was a piece of implied conditional. You had to basically go fetch the r. Given the a value in your conditional information in part D, you had to go fetch the r in order to be able to plug in and arrive at an answer. Now, I usually won't give you one that has multiple parts like this because I don't want to have to burden you with writing 4 sentences, right? But remember, asked in sentence form, answered in sentence form. So usually after this, once you work through your analytic work, you would actually write me a sentence showing me that you understand the import of that numerical answer. Okay? Now, this one's a fun one. A plate in the shape of an equilateral triangle expands with time. Okay, let's go ahead and draw the equilateral triangle. This is probably going to be awful, but let's see how close I can get. It's not bad, not terrible. Okay, so let's just pretend that that's an equilateral triangle, you know, that these are all the same. Yay. Now, okay, if it's equiangular and equilateral, then basically it looks like that. Now, I don't know if you remember the area formula for an equilateral triangle given the side, but basically it's just derived from a little bit of trig. If you basically drop an altitude down, remember that if this is equiangular, it's 60, 60, 60, which means that this becomes a 30, 60, 90 right triangle right here. Okay, and if this is x, if a side is x, then this right here is 1/2 x, and this is root 3 over 2x. Okay, now what that means is, remember that this is 1/2 x is already half the base, so the area of this triangle, of this whole triangle, is basically this root 3 over 2x times 1/2 x, and therefore it's root 3 over 4x squared. And you know it's good to know where it comes from, because this is the kind of formula, like I've said time and time again, easy to forget, right? But if you basically know how to drop an altitude and use a little bit of rudimentary trig, I mean, this is basically, I get these ratios of sides because it's a special right triangle, you know, 30, 60, 90 right triangle. And from there, of course, I can basically, this is half the base of the whole, so half the base times height is the area of a triangle, and then you just multiply those fractions. Root 3 over 2 times 1/2 is root 3 over 4, and then x times x squared. Beautiful. All right, now my given information is that the length of a side increases at a constant rate. So dx dt at 2 centimeters per hour. Now the question is, at what rate is the area increasing? So what is dA dt? So I kind of jumped the gun in giving you that formula because I hadn't actually gotten to that point yet. But, you know, I've read the question. So at what rate is the area increasing? What is dA dt when, conditional, when x is equal to 8 centimeters? Okay. Well, I have my area formula. That gives me the necessary relationship between the measurements, right? And now I simply have to differentiate to get the necessary relationship between the rates so that I can then, of course, relate the rates to each other. And I'm going to get dA dt is equal to root 3 over 2 times x times dx dt. I have an x, that's why I was given the conditional information. I have dx dt, so in order to find dA dt, I simply have to plug in. X is 8 centimeters, dx dt is 2 centimeters per hour. In terms of simplification, this 2 and that 2, of course, will cancel out, and I'm left with 8 root 3 centimeters squared per hour. And if you want to get a decimal approximation, that's probably a pretty good idea. Let's go ahead and 8 root 3, and that winds up being 13.856 centimeters squared per hour. And then, of course, you would write me a nice little sentence telling me the significance of that numerical answer that you've arrived at. Okay? Okay, let's go ahead and do one more on this video. A rectangle expands with time. The diagonal of the rectangle increases at a rate of 1 inch per hour, and the length increases at a rate of 1/4 of an inch per hour. How fast is the width increasing? When the width is 8 inches and the length is, when the width is 6 inches and the length is 8 inches. Okay, well, let's go ahead and draw this. Last time with width and length, I went ahead and used X and Y. This time, I'm going to use L and W. And it doesn't really matter. Basically, X and Y we're used to using, and therefore they wind up being easier in one sense. But length and width, since this isn't talking in terms of X and Y, it's talking in terms of length and width. Yeah, if you do it with X and Y, of course, you're constantly having to translate. You go, okay, it's talking about the width now. Now, which one is the width? Which one did I designate as width? But if it's L and W, it winds up being much easier, okay? And so what we have here is we have the given information. The given information is, and of course D is for diagonal, is dd dt. The diagonal increases at 1 inch per hour. And the length increases, dl dt, increases at 1/4 of an inch per hour. The question that I'm being asked is, what is dw dt? And I'm being asked for that piece of information when W is equal to 6 inches and L is equal to 8 inches. By the way, that implies that D is equal to 10 inches because it's a 3, 4, 5 right triangle at that moment, okay? Now, we're looking at L, we're looking at W, we're looking at D. We're not really looking at a rectangle. We're really looking at a right triangle, and we're really more interested in the Pythagorean theorem. And so this is what I meant earlier when I said sometimes the right triangle problems don't present themselves as Pythagoreans right up front. They're cloaked as something else because it didn't talk about triangles. Now, oftentimes, it doesn't talk about triangles at all, but it doesn't sort of give you a head fake by talking about something else, like a rectangle. And so you just have to recognize that basically inscribed within here is, of course, a right triangle. Not too difficult. So we get W squared plus L squared is equal to D squared. All three of them are changing. Notice that's why you didn't get a constant for any one of them. These, of course, are not constants. They are measurements at a moment in time. And so we're going to get 2W dW. Basically, all of these are going to have that coefficient of 2, right, when we differentiate. So we're just going to ignore that and give us W dW dt plus L times dL dt and D times dd dt. Well, if I'm looking for dW dt, then that's going to be D dd dt minus this quantity, right? Send it over to the other side. And then I, of course, have to divide by W. Now, that winds up being pretty easy. My D, remember, is 10 inches. My dd dt is 1 inch per hour. My L, my length at that moment in time, is 8 inches. And my dl dt is going to be 1/4 inches per hour. All of that over 6 inches. Now, inches as a unit becomes common to all of them. This winds up being 10 minus 2 over 6 inches per hour. That's 8 over 6, or 4/3 inches per hour. And of course, you would basically write me a nice little sentence explaining the significance of 4/3. It says, how fast is the width increasing? The width is increasing at a rate of 4/3 inches per hour at that moment, or something like that, okay? I have 3 more. We'll go ahead and do them in a separate video. As always, if you have any questions, shoot me an email. Bye.